Okay, now we're going to move on to number 6. I know number 5 was kind of confusing, so let's do number 6 together. We're doing the same thing. We are going to determine the possible positive zeros, negative zeros, and imaginary zeros, the possible number. Okay, so on number 6, the exponents skip from 6 to 3, but we don't have to worry about putting any zeros to hold the places. That's just in division. And I just need to make sure that it's in descending order, which this one is, so it's all good to go. So for my positive zeros, I'm just going to leave it the original polynomial. I'm not changing anything. I'm just counting the sign changes. So the first term is negative, second term is positive. That is one sign change. Second term is positive, third term is negative. That's one sign change. Negative to negative, that is not a sign change. Negative to negative, that is not a sign change. So for positive zeros, I could have 2 or I could have 0. Now I want to go back and substitute negative x in and simplify it so that if it is a even exponent, the sign in front is going to stay the same. If it is an odd exponent, the sign in front will change because the x will stay negative and affect that sign in front of the coefficient. So if it's an even exponent, the sign in front of the coefficient staying the same because that's going to be a positive x after you square it. If it is an odd exponent, then the sign is going to change. Constant numbers always keep the same sign. We're just going to count those sign changes in between each term in order from left to right. And again, I just have 2 sign changes, so I could have 2 negative zeros, negative roots, or I could have 0 negative roots. Okay, so now to determine how many imaginary roots I could have, the degree for the polynomial is 6, so when I am adding the possibilities across, it's going to total 6 every time. So if I have 2 positive and 2 negative, then I could have 2 imaginary. There's still room for 2 imaginary roots. And so that adds to be 6 as I go across. Okay, so if I have 0 positive, 0 negative, I could have 6 imaginary. Okay, so the thing is that the rule to decrease by 2's applies to imaginary numbers as well, or imaginary roots. So I could have also 4 imaginary roots. The reason being, I could have different combinations of positive and negative roots. For example, I could have 2 positive roots and 0 negative roots. That means I could have 4 imaginary. Or I could have 0 positive and 2 negative and have 4 imaginary roots. Okay, the point is not all the different combinations that you can get. The point is what's the most positive roots I can have and decrease that number by 2. What's the most negative roots I could have? Decrease that number by 2. What's the most imaginary roots I could have? In this case it's 6. Decrease that number by 2. So you could write it like this. Positive roots I could have 2 or 0. Negative roots I could have 2 or 0. Imaginary roots I could have 6 or 2, and you could include 0. I wouldn't count it wrong, even though in this case you're not going to have 0 imaginary roots, but you're following the rule. So as long as you're following the rule, decreasing by 2, it's okay if you have a 0 when you couldn't have a 0. So tomorrow, if we need to, we can go over another one of those problems, and if you're confused about that. But just follow the rule, find your highest number of imaginary or negative or positive zeros you can have, and decrease by 2's. Okay, so let's move on down to number 10. It says write a polynomial function with least degree and integral coefficients whose zeros include the following. Number 10, they give you 4 as a root, so x equals 4, and 4 minus I is a root, so x equals 4 minus I. So you had a real root and an imaginary root. Okay, the first sentence in the note says if a polynomial function has a complex number as one of its roots, which 4 minus I is a complex number, it must also have the conjugate of the complex number as one of its roots. So what that's saying is they are not going to give you the conjugate part. You have to know that it's there, and you have to add it on. So if they give me a complex number like 4 minus I have to add the conjugate of that, 4 plus I. So x also equals 4 plus I. And now I'm ready to find the polynomial. Okay, so I'm going to leave this x equals 4 alone right now, and I'm just going to work with those two complex roots. So I'm going to set them both equal to 0. So when I move them to the right side or to the left side, I'm going to subtract, and I'm going to put a parenthesis around 4 minus I and set it equal to 0. And then do the same thing with the 4 plus I. I'm going to subtract it, but I'm going to put parentheses around that 4 plus I because I'm subtracting the whole thing, not just the 4. I want to distribute the x. So my next step is to distribute that negative through the 4 minus I. I'm going to get rid of those parentheses. Okay, so x minus 4 plus I equals 0, and x minus 4 minus I equals 0. So I just distributed the negative through the parentheses, got rid of the parentheses, and I want to regroup. So I want to regroup where I have x minus 4 together. So x minus 4 is one term, and I is one term. And I have a pair of conjugates now. I have a term plus I and one term minus I. X minus 4 is one term, x minus 4 is one term. So they're identical first terms. So when I multiply those conjugates together, there is a shortcut method. First term is x minus 4, so I square the first term, square the last term, and subtract them. Forgot to put a square there. Okay, so when you square a binomial, just so happens the first term is a binomial, I have to FOIL them together. So x minus 4 times x minus 4. I'm going to get x squared minus 8x plus 16 minus, and I squared is actually negative 1, so this is going to be minus a negative 1, which is plus 1. Combine my like terms, x squared minus 8x plus 17. And now I'm going to take this trinomial times my last factor, or 0. So I want to set this x equals 4 equal to 0, and my binomial, the factor I get, is x minus 4. So I'm going to take this times that last trinomial. We have to just be very methodical about it and careful about our multiplication. X squared times x is x to the third. X squared times negative 4 is minus 4x squared, so I'm done with that first term. Negative 8x times x is minus 8x squared. Negative 8x times negative 4 is plus 32x, and I'm done with the 8x. Okay, my last number, 17 times x is plus 17x, and 17 times 4 is 68, so that's minus 68, and I'm done with this last term. So now I want to collect my like terms, and your polynomial is x to the third minus 12x squared plus 49x minus 68. And that is your polynomial that has the same factors.